Well, good morning and welcome. All right, let's take a look at some of these announcements. First of all, we're in Chapter 7 now. We only have 2 chapters for the rest of the semester. Chapter 7 is where we're going to spend the bulk of our time. Chapter 8, which is Dimensional Analysis and Similitude, will only actually have 1 class lecture devoted to Chapter 8, and there's no homework assignment. And so, Chapter 7 is sort of, you could say, highly represented on the final exam. So this is important material, and I'm glad you're here today. As I announced in the email that I sent yesterday, we're going to have a bonus quiz on Sunday the 15th of May. And the way that's going to work is the score you earn on that quiz will replace your lowest quiz grade of the semester. Maybe you already have 10, 10, 10 and don't need a bonus, but I think there are some students who will be glad for the opportunity. So in our class, we have the final exam on Thursday the 19th. And so my thinking behind having this bonus quiz being related to the older material is that you can start thinking about reviewing for the comprehensive final exam a little early and then apply those ideas for the bonus quiz. And then the last homework assignment you have due, 7B, that's on Tuesday, May 17th. And so that's our last class meeting of the semester. And then we have our final exam 2 days after. Okay, any questions about the announcements? All right. Like I mentioned earlier, I'm going to hand back the exams and show you the solution at the end of class today. Oh, for Chapter 8? Yeah. Well, what we're going to do for Chapter 8, which is Dimensional Analysis and Similitude, is we'll have an in-class exercise where we do problem solving here in the classroom. And it's pretty narrow what I need you to know from Chapter 8. And so I'm happy to do that. I'm happy to suggest problems from Chapter 8. But I think you'll have a very clear idea of what the topical coverage is just from the in-class exercise that we do. So I'm happy to suggest a few problems, and I'll post that information on iLearn. All right. So what we're doing now in Chapter 7 is we're starting to keep track of energy. So if you think of what we have in the last few chapters been focusing on, there has been conservation of momentum, which we did in Chapter 6, which is saying let's keep track of what flows in and what flows out in terms of the mass flow times the velocity. We've had conservation of volume when we did Q in equals Q out, which was the continuity principle. Now, what we're going to be looking at in the energy principle is ways to account for losses as flow goes between 2 points. And so if you think about the forces, the types of forces that we've encountered so far, like pressure at a certain depth acting over a surface area. That was a hydrostatic force. The gravitational forces that affect the pressure because it affects the depth, or the shear stress forces when we have an object moving through a fluid. When we start to consider losses, that opens up the range of problems we can solve, because in the real world, whenever fluids are moving, there are energy losses that have to be accounted for. And previously we've been using some simplifications that sometimes are okay, and sometimes the simplifications that we've had to use till now actually will give you a very different result if you were going to go repeat what you did on paper in the lab. So the new types of problems that we can solve when we start to keep track of energy losses, for instance, would be the amount of power required to pump fluids from one place to another, or the effects of pipe friction, because you remember that we have this thing called a velocity distribution, that when water flows through a pipe, that the velocity at the center of the pipe is the fastest because it's furthest away from where the friction is being applied at the edges of the pipe. And so this no-slip condition, which says that fluid that's right in immediate contact with a stationary surface is going the same velocity as that stationary surface, we can now start to say how much the pressure is going to be decreasing because of pipe friction. And that's very important, especially for large cities and designing the water networks there. We'll also be able to determine flow rates of fluids out of orifices because we've had the orifice equation in the past. You remember that the velocity from an orifice is v is the square root of 2gh. Well, not really. This would be the velocity of a jet coming out of an orifice if there was no energy loss at the orifice. If the water was perfectly flowing through that contracted opening without any turbulence, and it turns out that there actually are losses. And so we need to account for those losses so that we can have a more accurate idea of what the velocity genuinely is. And then there are things like pipe bends, at the elbow in a pipe or a valve, and all sorts of fittings that cause a reduction in pressure. And so we can account for all of these things and predict the effect of these kinds of variables on the pressure in a pipe network. So here we see the Bernoulli equation. Do you remember what are the 4 assumptions that we had to always keep in the back of our mind when we were using the Bernoulli equation? Okay, steady flow, good. An inviscid fluid. What does that mean, an inviscid fluid? A fluid with no viscosity. All right, so steady flow, inviscid fluid. What was the other one? Along a streamline and incompressible. Very good. So those are the 4 assumptions that we've made so far. And, sometimes it's true and sometimes it's not true. So the inviscid assumption is particularly troublesome because water is the most common fluid that we'll be dealing with, and especially as civil engineers, but water has viscosity. And so when water moves from point to point, there are energy losses. So this is the energy equation. It looks similar to Bernoulli. There are some subtle differences, though, that liberate us from those 4 assumptions that we had to make previously. So for instance, we now have this term at the end, H sub L. What that stands for is head losses. HL stands for head losses. And in fact, there are 2 components to head losses. Head loss, H sub L, includes H sub F, which is pipe friction, and H naught, which are called local losses. Now, the local losses are things like valves, fittings, a bend in the pipe. They happen in just one specific location. But pipe friction is distributed, which means that there is a certain length of pipe, and it's over a length that those losses occur. All right, so let's look at some of these other differences. Now, first of all, the pressure head term is the same. Do you remember what was one of our good problem-solving tools when we were applying Bernoulli equation? What would we try to do when we're picking where is 1 and where is 2? Like, what would make the most sense when we're applying Bernoulli's equation? What would we sometimes do in picking 1 and 2? Exactly right. So we'd want as many of these terms to be 0 as possible because we don't want to have an unspecified equation where there's too many unknowns. So for instance, if we had the orifice problem, where did we choose as location 1 and location 2 if we were going to apply the full Bernoulli equation to this tank? All right, so we have the first location be at the top of the tank, and what advantage do we have of putting it there? Okay, the pressure head term cancels out to 0. Usually we have some elevation measurement to the top of the water surface, so that gives us a Z1. Also, if it's a large tank, the water level may be falling, but it's not falling very far, and that enables us to neglect the velocity head term, V1. So the main point is we're going to try and pick locations where we know a lot of things. We know the pressure, we know the elevation, we know the velocity, because then that allows us to focus on those limited things we don't know at the second location. And so in the case of the discharge from an orifice, we'd have location 2 be just as the jet has come out of the orifice, because there again we know the pressure, we know the elevation, and our only thing we don't know is the V2. So we're going to use that same kind of technique when we apply the energy equation. And so you can see that the pressure head term is the same, and so your thinking should be the same. where can I choose as location 1 where I know a lot of things? All right, now let's look at this velocity head term, v squared divided by 2g. The first thing is you'll notice that there's an alpha term in front of that. That's called the kinetic energy correction factor. And on the next slide, I'm going to show you some more information about the kinetic energy correction factor. But here's the good news. Usually we just assume that alpha is equal to 1. It's under specialized conditions when it's anything other than 1. If you have laminar flow in a pipe, for example, then alpha equals 2. And for turbulent flow, usually alpha is around 1.03, 1.05. And so just for ease of calculations, it's commonly accepted to let alpha equal 1. So that's what the alpha means. Do you remember what v with a bar over the top signifies? Average velocity, right. So here we had velocity in the Bernoulli's equation, but that didn't mean the average velocity. Remember, we applied Bernoulli's equation at a point, at a specific point. So that means exactly here what is the velocity. So here, average velocity means that often we're applying this to locations in a pipe. You know, one upstream location in a pipe, a downstream location in a pipe. And so v bar means the average velocity. So it's the velocity not at a certain point in the pipe, but just in general, what is the average velocity for that place in the pipe. So that's what the v bar means. Z1 has the same meaning. H sub p is a pump term. And so if you're adding energy to flow with a pump, then the amount of head that you're adding to the flow in terms of meters, that's how you measure the head is meters, then that goes into the pump head term. And we'll work a lot more with pump head. So we've already talked about all of these terms over here on the right-hand side, except for instead of HP, we have HT, which stands for turbine. And a turbine is different from a pump because a pump adds energy, but a turbine takes energy out of the system. So if you're generating electricity, for example, then what a turbine does is it takes pressure from the system and it converts that pressure into movement inside of the turbine, which is converted into electricity. And so the amount of head that's extracted from the system and turned into electricity, that goes into H sub T. And I've already told you that H sub L stands for head loss. All right, there's one more thing about this equation that I want to tell you before we move on to the next slide. And that is, we have to be careful with assigning 1 and 2. It wasn't so much of an issue in the Bernoulli equation because both sides of the equation are the same. You know, you've got 3 terms on both sides. But now, on the energy equation, there isn't the same stuff on the left side of the equation as there is on the right side of the equation. And so 1 means the location upstream, and 2 means the location downstream. So you have to know what direction the water is flowing. And in this, our standard assumption is that the water is flowing from 1 towards 2. And that's very important because what we're saying is if the water goes from 1 towards 2, it's losing energy as it does that. That's why the water goes from 1 to 2, is because location 2 is a lower energy state. And so the flow goes towards where the energy is lower. For example, water flows downhill, right? Well, in a pipe, water flows from high pressure towards low pressure. And so energy goes towards the water goes towards the low energy state, and this H sub L, the head loss term, accounts for how much energy is lost between 1 and 2 due to the pipe friction and local losses. Now, we also need to keep in track 1 versus 2 because the pump term is adding energy. That's why it's on the left side of the equation, is because if you have water going from 1, let me just draw on the board here. If this is location 1 and this is location 2 and the water is going towards 2, here's how we draw a pump. The symbol for a pump is just a little circle with a triangle underneath. So the way to think about it is as the water is going from 1 towards 2, the energy is getting lower and lower and lower. But then there's a sudden boost due to the pump, and then the energy is going lower again after that. And so if you're keeping track of this accounting of energy, the pump head term needs to be on the left, and the turbine term should be on the right. Well, it will add the same amount of energy. The thing you need to keep track of when you're having a pump, you mean a pump, right? Not a turbine. If you are having a pump, then you remember we talked about cavitation? You want to have the turbine before the pressure of the water goes below the vapor pressure. So as long as you're avoiding cavitation, it doesn't matter if it's early or late, it adds the same amount of energy. It's just where you add the energy is dictated by avoiding cavitation. All right, so here's the energy equation again. We'll apply it to situations like this. Gigantic pipelines carrying, in this case, oil across the state of Alaska. So here is our terms again. Average velocity, head supplied by a pump, which has units of meters. Each one of these terms in the energy equation will have units of length. H sub T is the head that's given up by the flow to a turbine. H sub L has these two components. It's the local losses and the frictional losses. And then finally, alpha is the kinetic energy correction factor. So here's the situation with the kinetic energy correction factor. If you have a laminar velocity profile, this is parabolic shape because the flow conditions are laminar. If you just use the average velocity to calculate the velocity head, it turns out that you would be underestimating how much energy is actually there because this V is squared. Now remember, when we square something, for example, we had that problem where you double the diameter, you have 4 times as much cross-sectional area, right? So here, if we are just using the average velocity and squaring it, the problem is that then the highest point, this tip of the laminar profile, is being undercounted when you compare the predicted velocity head to the overall velocity head. And so the way that we can account for that is by calculating an alpha. And what we could do is we could take a differential area, a ring, around the pipe, because remember, this velocity profile is just sort of a cross-sectional view of what's actually bullet-shaped or cone-shaped. You've got a different velocity at each one of these radius away from the center. And so if you integrate that over the differential area, then long story short, for the laminar flow, the alpha turns out to be 2. For turbulent flow, it's about 1.05. So what we're going to do in most of these examples is just say, let's call alpha equals to 1. All right, I'd like you to get some experience with the energy equation today. And so what we have is a tank where the water is flowing from 1 towards 2, and some information is given about the tank. First of all, we know that the water surface elevation, that's what WSE stands for. That tells you the Z. So the water surface elevation here at 1 is 200 meters compared to 190 meters at tank 2. Now the water is flowing through 200 meters of 350 millimeter diameter pipe. And then there's one last thing. These head losses here have to be calculated empirically. We have to estimate the head loss based on there are so many different functions that have been developed over the years to try and estimate what are the head losses through a pipe. And one way of estimating the head losses through a pipe is to say the main variables that affect how much energy is lost due to friction is how long the pipe is and how fast the water flow is. And then you can put some number in front of that expression as a friction factor. So here, 0.04, you can think of that as an indication of how rough is the pipe. So the bigger the friction factor is, that means that there's a lot of roughness on the pipe, and so you're going to be losing more energy as the water flows through it. But then the overall head loss is proportional to the pipe length. So if you double the pipe length, then you double the amount of energy that's being lost through the pipe. And if you double the velocity, then the head loss is going to have, it's going to be quadrupled. Okay, so I'd like you to apply the information that's given here and find out the flow rate in the pipe. And one word of caution. So here's H sub L, a formula for H sub L. You're going to put that into the energy equation. You'll notice that there's a V. What V is this in the head loss? Because here in the energy equation we've got V1 and V2. It does, here in the head loss formula it doesn't say V1 or V2. So what V is it talking about? Partly. So you said the one in the middle, right? That's the velocity in the pipe. Because remember, our strategy is to pick location 1 to be where we know something and the location 2 to be where we know something. And so here we can choose location 1 to be in the reservoir. So we've got a reservoir connected to a pipe connected to a lower reservoir. So here's 200 meters of elevation. And that's location 1. Here's location 2, 190 meters. The formula for friction is talking about the velocity in the pipe. It's not saying V1 or V2. All right, so that's enough talking. Go ahead and get started on this one, and let's see if you can determine the flow rate, Q, in terms of cubic meters per second. The velocity in the reservoir. And it's a really big reservoir, and the water level's coming down. But it's coming down so slowly, you know, like 1 millimeter per hour, that you can neglect it, because if you put that into the velocity head term, it's going to be so small. Yeah. Anyone found the velocity or the flow rate yet? Let's see, 200, 190, squared. Yeah, that velocity's right, but it's Q is V times A. Yeah. So what's causing the water to move from location 1 towards location 2? Like, why is water going through the pipe? That's right. The elevation is higher. So it's obvious if you think about it. If you have a pipe that has water in it and you're connecting 2 tanks, the water is going to flow from one tank to the other until they have the same elevation. I mean, you can just sort of sense that somehow. It's intuitive. And so that's the driving force, as it's sometimes called. That's why there is velocity in the pipe. Now, over time, the velocity is going to be decreasing. If the water levels get closer together, you know, maybe after 2 hours or something, it's 190, like 198, and then it would be here 192, right? Because the water level is going up and going down. So the driving force is less, then the velocity is going to be less. Or conversely, here in the problem statement it says, what will happen if Z1 is raised? Well, if you have more Z1, then that's more driving force and the velocity would be higher. Did you have a question? Good question. Yeah, so what if one tank has a different diameter than the other? The only thing that would do is, let's say that this is a big tank and this is a small one. The water level will be rising faster in this tank than it will be falling here. But as far as, you know, at this moment in time, what is the flow rate and what is the velocity? It doesn't matter if one is big or one is small, because the only thing that we're looking at is the elevations at each. That's true. Yeah. Even if one is a big diameter tank and one is a small one. If we started the flow and then walked away, eventually they'll come into equilibrium. Are there other questions about this problem? So this is the type of thing that we're going to be solving with the energy equation. And Bernoulli's wouldn't tell us that, because Bernoulli's equation neglects energy losses between 2 points. Here, the energy losses have been accounted for with an empirical equation. An empirical equation is one that is not necessarily based on fundamental principles, but is based on observations of the data. So like this friction factor of 0.04. Probably just some engineer was doing lots of testing in the lab with this kind of pipe. Maybe this pipe is ductile iron pipe. And so this engineer was doing lots of experiments to find out how rough is the pipe and came up with a friction factor for it. One of the clues that you'll have that you're working with an equation that is empirical rather than fundamental is that the units often don't work out when you're working with an empirical formula. And here, if we look at length times velocity squared divided by 2g, so that would give us, let's look and see if the units do work out. The length is meters, the velocity is meters per second, and we're squaring it, so it's meters squared per second squared, and then divided by 2g. So that's 1 divided by, so it's meters per second squared. So in this case, we have meters to the cubed in the top, second squared, and meters. So we cancel that out. We have meters squared. So the units are just meters squared. And for head loss, it's supposed to have units of length. And so that's a clue that you have an empirical equation rather than a fundamental equation. All right. Mm-hmm. Yep.
The head loss equation that we had.
Yes. Yes.
That's all.
Yes. The diameter.
It was a larger diameter. Was it like the flow would be faster?
Yeah. The diameter is accounted for in this. And when you get into hydraulic engineering, when you take water resources, 341. Are you registered for 341 in the fall? Tomorrow. Okay. What you'll find out, H sub F, the formula that we usually use for hydraulic design is FLV squared divided by D2G. And so D does affect the head loss. Now here, they've combined the friction factor and the diameter into one expression. That 0.04 accounts for both. But more generally, the diameter does have an effect on not only the velocity, because if you have a big diameter, that's going to bring the velocity lower, but it also has a direct effect. All right, so water that flows through a pipe is doing work. And the reason for that, remember that force is pressure times area. Well, if we cut a pipe with our control surface, which we sometimes, as our technique from analysis, is drawing an imaginary line around something and analyzing what's happening on the inside, what's happening on the outside. If we cut a pipe with an imaginary line, then there's pressure on either side of that pipe. And so the water that's on the outside of the control surface is pushing towards the water on the inside. And so a pressure acting over an area is a force. And you accounted for that in momentum. Now, if you have a force acting over a distance, then that's work. Force times length is work. And water moving through a pipe has a change in force because there's a change in pressure as it goes through some incremental distance. As you go from point A to point B, which is some distance apart, delta L, and the pressure is being applied over that distance, then it's applying work. Now, we can account for the flow of work through a control surface by looking at the sum of all of the pressure times the velocity times the area. And the water that's on the inside of the control surface is having work done to it as it flows. And what we have to remember is that there's friction losses. As the water flows through the pipe, the pressure is going to be decreasing because of the pipe friction. And so you can think of that as work that the fluid is doing on the pipe itself. And so part of the energy loss could, there's different ways to account for it, but you can think of the loss that you're experiencing in pressure is because of the work that the flow is doing. So what are the units of work flow? If we looked here at the units of the three components, the pressure is newtons per meter squared, the velocity is meters per second, and area is meters squared. So what's left is, if we cancel out these terms, meters squared, Newton meter per second. What is a Newton meter? Do you remember from physics? A Newton times a meter is a joule. Okay, so we have joules per second, which is the same as watts. Okay, so the units are units of work, as they should be. Now, that was flow work. Water flowing through a pipe is doing work as it exerts forces. There's also shaft work, and we've already talked today about pumps and turbines. And a pump is doing work by increasing the pressure inside of the pipe. It's adding energy to the system. And similarly, a turbine is removing energy from the system. And so the flow is acting on the turbine, and we can extract that energy and turn it into electricity. And so they're sort of inverses of each other in the way that they work in the energy equation. If we get really specific and technical about it, we can even keep track of how much energy there is in the fluid itself. And sometimes, especially in the case of chemical engineering, when you're pumping fluids that are flammable, you can think of the amount of energy that exists, the chemical energy, the heat energy, and then also look at the kinetic energy as you lift fluid from place to place, adding that's the potential energy. So in steady state, the energy equation grows to include the work that's being added to the system and how much of that work remains at locations as they move through place to place. And since we're running low on time, we're going to have to leave it at this slide before I give back your exams. All right. Energy is measured in joules, and here's the energy equation. Work also has units of joules. And energy is used to perform work. That's sort of how we distinguish between the terminology. Although they have the same units of accounting, if we're going to just think about the language of how we use energy and work, this is maybe the simplest expression of that. Now power is when we add the time dependency there. How many of you have seen the signs that they have next to elevators where it says that you should take the stairs because it will save electricity? Yeah. Right. Yeah, burn calories, not electricity. I think if we looked at those signs, the units are wrong. Because they're saying kilowatts per hour, right? I think what they maybe mean is kilowatt hours. So kilowatt multiplied by hours, not kilowatts divided by hours. So, yeah, yeah, that doesn't surprise me. All right, so power is when we're saying how much energy is being used per time. And so how many joules are being expended per second, or in the case of a turbine, generated per second. And so the units here are watts. And if you take the flow rate in terms of Q, so that would be cubic meters per second, and the unit weight of the fluid, which is newtons per meter cubed, and then you multiply that by the pump head, if you're talking about a pump, or the turbine head, in the case of a turbine, then you can get power from that. And power is going to be in units of watts. And so this is the power equation. Now, as it's written on the screen here, it's assuming that there's no losses, that there's no energy losses. And when we get together on Sunday, we'll talk more about the power equation and how efficiency factors in. All right, for now, what I'd like to do is show you the solution to the exam.